In this brief video, I'll be introducing how to do data exploration and data visualization with histograms. In this video, our example data is going to be from Francis Galton, and it is on the heights of families in order to understand the heritability of human height. There's a previous video introducing these data. So data exploration and data visualization tools are really important for modern data analysis because they allow us to understand the variability of data and what we call the distribution or the shape of the data. Is the data really pointy, or is the data really consistent, or is it spread far out? Is it skewed from one direction to another? All of these things are really important to understand when you're doing data analysis yourself. It's also really important to present it somehow to anyone who reads a paper you write or a report that you put together. So histograms are probably one of the best tools for summarizing variation in data. In subsequent videos, I'll talk about some other options, but histograms are really, really useful. They probably should be made more often. Unfortunately, they're a little bit tricky to make in most spreadsheets, and specialized software is better for making them. So how do we understand a histogram? The x-axis of a histogram is a continuous numeric variable. So this is the height that Francis Galton was measuring with his ruler. And the y-axis is a count of the number of individuals that had each one of the values along the x-axis. So the x-axis is the actual measurements that were being made, and the y-axis is a count or a tally of the number of individuals that had those measurements. So let's get a little bit more specific exactly how histograms are made. Let's look at the raw data. What we can do is we can place each measurement into what we'll call a bin, and we'll use 1-inch bins, which work well for this data set. So First, we'll start off and we'll make a 73-inch bin. Recall that Galton requires us to add 60 inches to each one of the measurements he listed. So if we look at values that are between 13 and 13.9 inches, those are actually meant to represent around 73 inches. So we have 13.2, 13.5. We'll add 60 to them. Those are 73 inches approximately. So that'll be our 73-inch bin. We'll also make a 8-inch bin, or rather a 68-inch bin. We'll find all our values that are around 8 inches, 8.5, 8, and 8. We will add 60 to them, and we'll make a 68-inch bin. And then we could do that for all the other values in the data set on each page. So let's imagine that we did this in our spreadsheet or with our specialized software. We can make a list of all of our bins. For this, the daughters, the data ranged from about 56 inches on the low end to about 70 inches. We're ignoring, again, the precise values, and we're just counting up the number of individuals that fell into the 56-inch bin, the number of individuals that fell into the 70-inch bin. For example, this is the 68-inch bin, which we were looking at, and if we go through all the data sheets, there were 25 total XX individuals, 25 total daughters that fell into this 68-inch bin, or their original measurements were between 68 and 68.9 inches. We can then plot the data like this. And we'll be looking at comparing the daughters and the sons, the XX and the XY individuals, against each other. Again, it is the height of the individuals along the x-axis, but it's not the precise height. Each one of these values along the x-axis is a 1-inch bin or a 1-inch range. So that's 60 inches, 61, and so forth. And the y-axis is the number of individuals in each one of those bins. So precisely how to read this, all of the data are represented or summarized in the histogram and represented by the heights of these bars. So for example, this bar here, if we trace down to the x-axis and count over, this is the 65-inch bin, 66, 67, this is the 68-inch bin. We look over at the height, we trace that to the y-axis, and this is the 25 value along the y-axis. So there are 25 total individuals that were counted up in our 68-inch bin. Where there are no bars, that means there were no individuals that fell in here. So there was only one individual in the, it looks like the 56-inch bin. There were a lot of individuals in the 64-inch, but 0 in the 75-inch bin. Then we can compare that. We can compare the range and distribution to the XY data over here. We can see that there were individuals in the 75-inch bin over here. So this is one way we can compare the data. What are other things that you can learn? Well, one of the first things, as I just did, is you can take into account the range. The range is just the difference between the lowest value and the highest value, or in this case, the lowest bin and the highest bin. So 55 to 70 inches, that's about 15 inches, depending on exactly how you want to do the math. But for our purposes, a 15-inch range is sufficient. And then we could also do this for the XY data, and we can compare the range quickly visually, as we did a moment ago, and see that the range is quite a bit larger in the XY data. The median is another important value that's often displayed on histograms. There's a little bit of math required to calculate the median exactly. We won't worry about that, but with the raw data, it's the middle value or the approximate middle value. And often it's this is drawn. It should be approximately visually between the highest value and the lowest value, though it's not necessarily going to be going through the highest bar. Here, in this case, the highest bar here is the median. In this case, though, the median is slightly below the highest bar. So in humans, we can look and say that in XY females, the median is about 64 inches. In XX males, in XX females, it's about 64 inches. In XY males, it's about 69 inches. And we can make conclusions from that about the relative height difference between. So XX females are, in this data set, have less height, lower height than XY males. So the mean is another common value sometimes placed on it. It's the average or arithmetic average. It describes the center of the distribution. When distributions are symmetrical, when they're nice and symmetrical on both sides of the mean and median, the mean and the median are usually pretty similar. The more skewed in one direction, the more stretched in one direction or another, the mean and median are going to be further apart. The mode is the most common observation, and this is easy to spot on a histogram. This is just the tallest bar. And as we've seen already, the mean, median, mode are also always slightly different. And again, if the data is perfectly symmetrical, then the mean, median, and mode will all be about the same. But if the data is skewed in one direction or another, then those values will be different. We started off talking about that we're often looking at histograms to understand variation. We can quantify variation if we want, and we frequently do, using what's called the standard deviation. The standard deviation is in reference to the mean. The median does not go along with the standard deviation. The mean goes along with the standard deviation. And we often talk about how much data is between +1 standard deviation and -1 standard deviation. And the general model is that when the data is relatively normally distributed, relatively bell-curved, then about 68% of the data are, we would say, ±1 standard deviation of the mean when the data is normal or when it's following a symmetrical distribution. So knowing just the mean and the standard deviation, if the data are fairly normal or bell-curved, that gives us a sense for the distribution of the data. But we can only really know everything about the data, the full distribution of the data, if we look at the histogram itself. It's important to know biological data are almost never truly symmetrical or normal, and that's so important it really needs to be repeated. The normal distribution, the bell curve, we call it a model. It's a simplification. So the standard deviation, calculating a standard deviation for biological data, is a simplification. You're going to be making some assumptions. It's frequently done, but this is why, because data is rarely normal in biology. It's really important for us to plot the raw data to make histograms. We can talk about the mean and standard deviation, but it's really important for us to also look at the raw data or to look at the data in the histogram in order to understand the distribution. When we do calculate the standard deviation, we can compare them to look at whether two groups are similar. So you can look at these data and you can eyeball it and you can ask yourself which one would have the larger standard deviation. It should be that the blue, the X, Y on the right, males should have a larger standard deviation. So we could, which represents the larger amount of variation in the data. So we could summarize numerically what's shown in the histogram with that number. But again, it's always best to show the data in a graph like this.